स्पेस के एनी पॉइंट रिप्रेजेंट्स अ मोड. ठीक है. फॉर एग्जाम्पल दिस पर्टिकुलर मोड इज ऑन दी YZ plane. It has an nx value of 1 2 3 4 5 and y value of nx value of 0 and y value of 5 and nz value of 1. Likewise, you can make points at any point in the you can identify modes at any point in the space. Agreed? And only modes exist at these fiducial points, at these points, not in between, because the modes can only take up integer values of n. Now each mode is represented by a small cube. अगर हम काउंट करना चाहें मोड्स की तादाद, it is represented by a small cube. This equation that I've written above can also be written in this form: E naught sine KYY sine KZ Z sine 2 pi ft, where kx is nx pi over L, ky is ny pi over L, and kz is ng pi over L. आपने waves and oscillations में पढ़ा होगा कि you can define a wave vector k. Now don't confuse this with the Boltzmann constant. You can define a wave vector k which is given by 2 pi over lambda. ठीक है, पढ़ा होगा ना आपने. Standing wave के लिए आपको पता है कि L has an integer number of half wavelengths, n lambda over 2. So let me write pi here. Let me write pi here. N over k. 2 pi over lambda is k. K is pi n over L. So I've exactly used this identification here in defining kx, ky and kz. ठीक है, ये वाला मैंने फॉर्मूला यूज किया इस को डिफाइन करने की. बिल्कुल एग्जैक्टली एनालोगस है ना ये. ठीक है. So these are the components of the wave vector. What is the wave vector? कोई मुझे बताए कि wave vector फिजिकली क्या चीज होती है? Anyone? What is the wave vector? We know what is the frequency. We know what is the wavelength. First of all, question: is the wave vector a vector or a scalar? Scalar. तो फिर इसके components का क्या मतलब? बिल्कुल सही. The wave vector tells you the direction of propagation of the wave. ठीक है. The wave, कोई भी wave transmit हो रही है, उसकी direction of propagation क्या है? So it must be a vector. It is defined by these three coordinates: kx, ky and kz. So k is in fact a vector. K is given by kx I plus ky j plus kz k. ठीक है. तो ये एक वेक्टर है दरअसल के, जो डायरेक्शन ऑफ प्रोपगेशन ऑफ वेव बताता है. ठीक है. Which means that k squared, since it's a vector, k squared is kx squared plus ky squared plus kz squared. Agree? But what is k squared? K squared is 4 pi square over lambda squared. ठीक है. So we can write this as 4 pi square. Lambda squared is nothing but c squared f squared, and this is k squared. So the square of the wave vector, the scalar, now k squared is a scalar, ठीक है, ये इसके length of this vector है ना k, length of the wave vector is k, is given by the squares of the components, must be given by 4 pi squared over lambda squared from the definition of the wave vector. K is 2 pi over lambda, so k squared is 4 pi squared over lambda squared. Lambda we already know is c over f. Simple wave motion से आपको पता है कि speed is wavelength times the frequency, so k squared is this number. But we also know that k squared must be given by the square of these terms. So k squared is 4 pi squared f squared over c squared is given in fact by pi squared l squared and x squared plus n y squared plus n z squared. I am only doing algebra with a little bit of physical motivation at each step. ठीक है, तो algebra की तो समझ आ गई आपको, physical motivation की समझ आ रही कि what am I doing? Now what is my purpose of doing all of this? The purpose is I want to find the number of modes with frequency less than or equal to f. Question. The question is number of modes with frequencies less than or equal to f. How many modes, such modes exist? So let's move to this diagram. ठीक है, इसमें हर मोड, ये 3-dimensional space है, इसमें एक मोड के साथ एक वॉल्यूम एसोसिएटेड है. ठीक है, एक मोड, what is representing a single mode here? A cube. A cube, a small cube at this point is in fact one mode. Every mode is being represented by a unit cube. Every mode is being represented by a unit cube. Now if I want to find the number of modes with frequency less than or equal to f, what do I need to do? I have to count the number of cubes which are within a volume. So, and the volume is to be taken such that the outer surface of the volume corresponds to the frequency I am trying to, the frequency f. I have to make a certain surface on this space and find the volume of that surface and count the number of cubes in that surface. Now we already know that f and n's are related. So ये जो terms हैं ये उस diagram से आ रही हैं, और f is our frequency of interest, which means that f squared is pi squared l squared c squared 4 pi squared. 4, you get the pi's cancel out. And x squared plus ny squared plus nz squared. So this is the relationship between the n's and the frequency. And I'm going to redraw this figure a little bit to make it a bit clearer. अच्छा ये जो मैंने स्पेस बनाई है, इज इट रियल स्पेस? ये x एक्स, ये इसकी डायमेंशंस क्या हैं? ये nx, ये इसकी डायमेंशन डिस्टेंस की है, किस चीज की डिस्टेंस है? जस्ट पॉइंट्स, नंबर ऑफ पॉइंट्स. Okay, so we have 1 2 3 4 here, 1 2 3 4 5 here. These are integer points, so it's a discrete space. It's not a continuous space, it's a discrete space, and this is called the n space. ये real space नहीं है, ये distance x, distance y, distance z नहीं है, ये nx, ny और nz है. ठीक है? अब अगर मैं एक sphere बनाऊं, if I make a sphere and I can measure the volume of the sphere, and the volume of the sphere will be given in these discrete units. इसका मतलब ये है कि I can measure the volume of the sphere in this discrete space. Because one dimension में, जब हमने one dimension की बात की, तो आपने number of points count किए थे with frequency less than or equal to f. इसमें you do not measure length, you measure volume. Now you draw a sphere in the n space. What will be the volume if n is the radius? If n is the radius, अगर n radius है, you can draw a sphere of volume 4/3 pi n cube. You can draw a sphere of this volume. Okay, where n is the radius, but n's can only take up positive values. So you have to find not the volume of a sphere but of an octant, of the positive octant, क्योंकि n की वैल्यू सिर्फ पॉजिटिव हो सकती है. So you divide this by 8. You have pi n cube over 6. So this is the number of points. This is the number of small cubes within an octant of radius n. Why did I divide by 8? यहां तक समझ आया? 4/3 pi n क्यूब. ये स्फीयर का वॉल्यूम होता है ना, n स्पेस में स्फीयर का वॉल्यूम यही होगा, फिर n is the radius. This radius is n. ठीक है, the radius is n. Now I draw a sphere. The sphere has a volume 4/3 pi n cube. But when we talk about modes, when we are talking about the physical situation, the modes can have only positive values of n. The modes can, when we talk about the electric field, k's and n's, nx, n pi, ny, we've already mentioned that they can be from 1, 2, 3 and onwards. They're only positive. So we can't take the volume of the entire sphere. We have to take the volume of the octant, the positive octant. Octant समझते हैं? एक sphere है, ठीक है, उसको 8 हिस्सों में डिवाइड कर दें, तो एक हिस्से में सारे nx, ny, nz पॉजिटिव होंगे. इस तरह क्वाड्रेंट होता है 2 डायमेंशंस में. अगर आप 2 डायमेंशंस में प्लॉट करें nx, ny, only this region of space, only for this region of space will nx and ny both have positive values. In 3 dimensions you talk about an octant. 8 हिस्सों में डिवाइड कर दे स्फीयर को, तो एक ऑक्टेंट आपको पॉजिटिव वैल्यू देगा तीनों नंबर्स की. जी
सर, ये तो हमने लेकिन वो कंटिन्यूअसली सॉलिड बॉडी की हमने वॉल्यूम निकाली है, बट फॉर इंडिविजुअल पॉइंट्स ये क्योंकि एंड्स जो है ये तो डिस्क्रीट नहीं है, नंबर ऑफ पॉइंट्स जो है.
हाँ, ये देखें, ये जो n है, n is a volume, n is a radius. Now we have to choose our radius. And where do we get our radius from? Our radius comes from here. अच्छा, पहले बात समझ आ गई ऑक्टेंट की, ठीक है? So this is the volume of the octant. If you look at this expression, what is this? This is n squared. In the 3-dimensional n space, this term is n squared. nx squared plus ny squared plus nz squared. n squared, c squared, 4L squared, which means that the relationship between f and n, we really want to find the relationship between f and n. The relationship is f equals nc over 2L. देखो ये सारे काम हमने इसलिए किया so that we have a relationship between n and f. So this is our relationship. This is the number of points or the number of modes within an octant of radius n, and the number of modes with frequencies less than f will simply, you will put in the value of n here in terms of f. You will count the number of modes which have frequencies less than f. n की जगह आप ये डाल देंगे 2LF over c. So the answer to this question is pi over 6. N is 2LF over c. N is 2LF over c. 3 raised to power 2. Okay. So this is the number of modes with frequencies less than f. So you will find the most positive integer n with a value smaller than what you get. Okay. Okay, this is the volume of an octant of radius n. Okay, complicated stuff, so please pay attention. A volume of an octant which gives you the number of modes with frequencies less than f. Now we want to find the number of modes in a small frequency interval. That's what we want to do, because our density of modes is defined as the number of modes per frequency interval. So what do? We take this volume and instead of talking about the volume, we make a shell. We make a small incremental increase in our distance from the origin and make a shell. एक मिनट होगा. हम एक 3 डायमेंशन में शेल बनाते हैं. मैं उसके ऊपर वाली सरफेस नहीं शो कर रहा. ठीक है, यू आर फेमिलियर विद सॉल्विंग प्रॉब्लम्स ऑफ दिस काइंड. यू हैव अ वॉल्यूम and then you find a small incremental volume. You find a small incremental volume. If your volume is this, then your small incremental volume will simply be 3 pi n square over 6 dm. देखो ना, ये n क्यूब है ना यहां पर. ठीक है, तो n सॉरी 3 आएगा. थैंक यू. अच्छा, हमने ये वॉल्यूम बनाया और उसके ऊपर एक छोटी सी परत, एक छोटी सी तय वॉल्यूम, एक छोटी सी शेल बनाया. ठीक है, इट्स एन इंक्रीमेंटल वॉल्यूम, इट्स अ स्मॉल शेल, एंड द डिफरेंशियल वॉल्यूम ऑफ दिस शेल विल बी गिवन बाय दिस. Now, how many modes exist within this dV? How many modes exist within this small volume? We know what dN is. We know the relationship between F and N, and the relationship is N equals 2L over CF. So dN will equal 2L over C dF. वन बाई टू. देखो ना, 3 इसको डिफरेंशिएट किया, 3 पाई n स्क्वायर आ गया. ठीक है, so this is a relationship between f and n from here. So dn equals this, which means dv will equal pi n squared over 2. dn is 2l over c df. एक मिनट all right. So this is the differential volume. This is the volume of this small shell. And what will be the units of this volume? Number of points. Number of points. So the number of modes within this shell will be given by this expression. The number of modes within this small volume, that is the number of modes that exist in a frequency range df, centered at this value of n, will be given by this expression. Hence, number of modes at frequency f within an interval df, that is between f and df and f plus df, is given by pi over 2 L n squared df. It's just this incremental volume, and you multiply this with 2, because for every propagation direction there are two kinds of polarizations that are possible. Agreed? For every propagation direction, for every direction of k, there are two possible polarizations. So you have to multiply by 2. So the expression that you get is pi L. Now we have to replace n squared by a frequency 2L over C squared, and df by df remains df. 2LF. यहाँ पे थैंक यू। n की जगह हमने 2LF over C square दिया। So this is the number of modes in a frequency interval df at the frequency f. This turns out to be 2 pi L cube C cube 4 f squared df. Eight pi L cube f squared over c cube df. So this is the number of modes within the frequency range df at the frequency f. So what is the density of modes? G, it's a function of f now. Gf is a function of f. The density of modes, the number of modes in a frequency interval df per unit volume. This is just the volume. L cube is just the volume. So Gf turns out to be 8 pi f squared over c cube. It's a very important result. It explains the conductivity of electrons in metals. It explains the specific heat capacity of solids. It's a very important result. It tells you the number of modes in a frequency interval. So what will now rho be? It will be this number, Gf multiplied by the average energy of a mode. G.
How did you get from the df term 8 pi L cube f square over c cube to that 8 pi f square over c cube?
यहाँ से इधर कैसे आया? इधर से इधर? ये नंबर ऑफ मोड्स है ना? In df. So the number of modes per unit frequency will be this number, 8 pi L cube f squared over c cube, and you divide by the volume, you get 8 pi f squared over c cube. Okay, very nice question. बॉल पॉइंट्स को प्लीज क्लिक ना करें.
तो ये आवाज
अच्छा, इन्होंने सवाल ये पूछा है कि why are we dividing by volume in space here? देखो L cube is the volume not in n space, it's the volume in the real space. Why are we dividing by the volume in real space? Because energy density is defined as the number of modes or the energy per unit volume in the real space. That is why we have to divide by the volume in real space, by the volume of the cavity, not the volume in n space. If you remember, sometimes we're talking about the real space and sometimes we're talking about the n space. They are two different concepts. So this is our density of modes. And what is the average energy of each mode? kT. The average energy of each mode is kT. So the spectral energy density is simply given by 8 pi f squared c cube kT. Now I am writing a small b with k to identify it with the Boltzmann constant. So this result was derived by two scientists, Rayleigh and Jeans. Does this result describe our function? Does the result describe our function? Is it a good fit to the function? Not at all. Because the Rayleigh-Jeans function increases with f and it keeps on increasing unchecked. With increase in F, the spectral energy density goes on increasing. So it's a very bad calculation, and we spent 2 lectures on deriving a result which does not work. And what this result actually shows is that if you increase the frequency, the energy density goes on increasing. So if you open an oven, at a certain temperature, you will be instantly killed by ultraviolet radiation, because the energy density is increasing for higher frequencies. And this is what is called the ultraviolet catastrophe. But the result does work well for small frequencies. The result does indeed work for small frequencies. So there was a long list of scientists now, Rayleigh Jeans, Wien, most notable of them, who looked at different theoretical explanations that could describe the entire spectral radiance curve appropriately, both in the high frequency regime and in the low frequency regime. Rayleigh Jeans formula only works for the low frequency regime, and what has been derived so far does not use any quantum mechanics. It uses purely classical thermodynamics and classical electricity and magnetism. No quantum theory has yet been knocked at. Quantum theory has not entered the picture because Mr. Planck has not yet entered the picture. जब प्लैंक साहब तशरीफ लाएंगे तो वो इस थ्योरी में ऐसा गेस करेंगे कि जो एक्सपेरिमेंटल कर्व्स हैं ये अप्रोप्रिएटली और एक्यूरेटली डिस्क्राइब हो सके बोथ इन द लो फ्रीक्वेंसी regime as well as the high frequency regime, and that is where quantum theory was born. Planck corrected this formula. Planck corrected this formula in the year 1896. He spent 6 years on working on this formula, and there were 200 years of experimentation behind this. वो गुमनाम सिपाही हैं. प्लैंक को सारा क्रेडिट दे दिया जाता है कि he was the originator of the quantum theory because he had spent 6 years mathematically describing the spectral radiance curve. Now, how did Planck guess the correct formula? And how did it give birth to quantum mechanics, to the idea of quantization? That's what we're going to learn in the next 15 minutes. अब सबसे पहले तो ये बात देखें कि this spectral density function, energy density function, contains 2 parts. It contains a density of modes and it contains an average energy. Now this average energy is independent of frequency in the classical picture. ये frequency पे depend तो नहीं कर रही, ये सिर्फ temperature पर depend कर रहा है. तो प्लैंक का कारनामा ये था कि he wants some average energy, let's call it U, some average energy. Classical physics tells us that U is independent of frequency. Planck thought that this U must not only depend upon temperature, it must also depend upon frequency. Because Rayleigh-Jeans formula works for the low frequency limit. So he did not want to touch the Rayleigh-Jeans formula because it gave correct results at low frequencies. The problem arose for higher frequencies. He wanted to have a U, an average energy function that depended on frequency as well. So what he wanted to do was something like this. A U is now not only a function of temperature but of frequency as well. In the low frequency regime, he wanted this to be exactly equal to kBt, so that Rayleigh-Jeans result could be reproduced. But in the high frequency regime, he wanted this function to gradually approach 0, so that the spectral radiance curve does not go up unbounded, yet it asymptotes back to 0. And if you guess something, a nice candidate for this U, just out of pure guesswork, could be an exponentially decaying function. Just out of guesswork, kBt exponent minus something, just write A F over KBT. Something similar to this, because here as F goes up, the whole term disappears. So an exponential function would be a good candidate for Planck's quantum correction. Now this is what we're going to study now. It's going to be brief, but this is a slightly more, this is another complicated part of our course, and as I've mentioned, these two lectures are the most complicated and terse part of what we'll be studying in this course. Anyways, let's see how Planck came up with his correction. All right. Now, Rayleigh-Jeans ideas. I think I have to speak very loud, and because this thing is so. All right. Classical physics is based upon, and Rayleigh-Jeans innovations were based upon what is called the Maxwell-Boltzmann distribution. Suppose you have energy E, and energy goes from 0 to infinity. Now, if there is a system with a large possibility of energy, what is the most probable state? देखो, अगर एक सिस्टम है वो लो एनर्जी में भी एग्जिस्ट कर सकता है, हाई एनर्जी स्टेट में भी, हायर एनर्जी स्टेट्स में, व्हाट इज द मोस्ट प्रोबेबल? द लोएस्ट एनर्जी स्टेट. So the Maxwell-Boltzmann distribution tells you that if you have energy on one axis and the probability that the system has energy E on the other axis, then this will be a decaying exponential. So the highest probability is at the lowest energy, and as the energy increases, the probability of a system possessing that energy decreases. That's totally classical result. ठीक है? And this PE, the Boltzmann distribution says that this PE is 1 over KBT exponent minus E over KBT. This is the probability of a system possessing energy E. It's an exponentially decaying function. Now, how do we find the average energy of a system? क्योंकि हमने मोड्स में देखा, here we are using the average energy of the system. And we look, now we're going into more details of where this KBT comes from. How do we find the average of something? Suppose you have a dice. ठीक है, आपके पास एक लुड्डू का दाना है, 1 2 3 4 5 6. What's the average number that you will get in a statistical process? 3.5. That's the average you will get. What will you do? You will take the number 1, multiply it with its probability 1 by 6, plus the number 2, multiply it with its probability 1 by 6, and so on. So you will take each number, multiply it with its probability, which is the same as taking the average, because all of these are equiprobable events. So in order to find the average of something, which is called the expectation value, in order to find the expectation value of the energy, the expected value of the energy, what you have to do, you have to multiply the probability of energy with the energy itself. and with the energy itself, and this will give you the average value. So if we plot a graph between E and PE and this value, then the graph will look like this. Okay? Alright, so this is the graph between E, PE and E. Now, if you take the area under this curve, that will give you the average value. देखो एवरेज वैल्यू क्या है किसी चीज की, x की एवरेज वैल्यू क्या है, x multiplied by px, and if there are different possible values of x, xi, pxi, take the sum and you divide by pxi over all possible values of I. This is just for normalization. If this pxi is not equal to 1, you have to divide it by pxi. So this is the formula for the average of something. ठीक है? You multiply the variable with its probability and add up everything. If this is 1, you don't have to put in a denominator here, because the sum of probabilities has to be equal to 1. So how do we find the average value of the energy? देखो एनर्जी की एवरेज वैल्यू कैसे फाइंड करेंगे? You take E, multiply it with PE and take the integral over all possibilities of E, and you can also divide by but in our case this is equal to 1. If you use this formula for PE, you will find out that this integral is equal to 1. Now what is this integral? This integral is just the area under this curve. And if you put in the value of PE, that is E exponent minus E over KBT over KBT dE, the answer that you get is KBT. Then go home and solve this integral. So the average energy, classically calculated average energy from the Maxwell-Boltzmann distribution is KBT, somewhere here. And this is the energy that Rayleigh engines used for the average energy of a mode. Now what did Planck do? यहाँ तक बात समझ आ रही है कि अभी तक हमने we've done everything classically. We've looked at the probability versus energy curve. We've looked at the product of the energy and probability versus energy curve. We found out that the area under this curve has a certain value which is given by the average energy, and that is equal to KBT. Integral area एक ही बात. देखें ये आखिरी 10 मिनट है, बहुत इंपॉर्टेंट, बिकॉज दिस इज द कल्मिनेशन ऑफ द लेक्चर, सो प्लीज पे अटेंशन. ऑल राइट, energy lies somewhere here. Now this is a continuous curve. This is a continuous curve. Continuous curve है ना? Energy की सब values possible है. Energy can take up any value, and the area under this curve gives you the average energy. Now what Planck did? Planck supposed that what if we replace this integral by a discrete sum? That is, the energy does not take up continuous value. Instead, he supposed that the atoms of the balls which are in contact with the cavity, they do not have all possibilities of energy. Rather, the energies are quantized. That is, E can only take up certain values. E is given by 0, HF, 2HF, 3HF, and so on, up to infinity. So we have a cavity. The walls of the cavity are made up of atoms. These are atoms. And these atoms are like harmonic oscillators. And these oscillators have frequencies F. The frequency is given by, everyone knows, the spring constant divided by the mass square root. Okay? But the energies are not only HF, they are HF, 2HF, 3HF, 4HF, and so on. So that the energy of this oscillator is quantized, and when it oscillates in a quantized mode, the radiation also has quantized energies. So if the oscillator is oscillating with 4HF, the radiation has a frequency 4HF, or has an energy 4HF. If the oscillator is oscillating with the frequency 5F, the energy has and the radiation has an energy 5HF, and so on. So that the energy is now quantized. Let me finish because we're short of time. So what Planck did, he quantized the energies through a quantization of the atoms making up the cavity, and hence a quantization of the energies of the electromagnetic radiation. So what he really did, now delta E, that is the frequency separation between two successive quantization, is given by HF. Now if this HF is much smaller than KBT, that is the frequency is so small that HF is much smaller than KBT, then this curve is in fact, these are rectangles, these are small rectangles. इस तरह के बहुत से छोटे छोटे rectangles हैं. Planck suggested is that this is not a continuous curve, rather it's a discrete curve. There are small rectangles that make up the energies. The width of each rectangle is HF, and there are many of these small rectangles. If HF is less than KBT, then the width of each rectangle will be very small, which means that if frequency is small, if F is small, then the sum of the area of these rectangles rectangles will be the same as the sum of the continuous curve. And therefore, Rayleigh Jeans result that the average is KBT will be reproduced. Okay? However, in the other extreme case of when HF is much larger than KBT, let's see what happens. We have E here, we have EPE here, we have this curve. Now HF, the width of the first rectangle is very large. Suppose this is KBT. The first rectangle is very large. So the first rectangle starts from somewhere here. This is empty because the first frequency is 0. That is, the first energy is 0 because energy starts at 0. So the first rectangle has 0 height. So this distance or this span is HF. The first energy is 0, which means that the first rectangle must have 0 height. And the first frequency is F, which means the first energy is HF. So after a span of HF, then the first rectangle appears. And this rectangle will have a height given by the Boltzmann distribution. But now it's not a continuous sum. You take this. In fact, this will go like this, because we have this span is also HF. Then you take the next rectangle, and then you find the sum of these rectangles, the area under these rectangles, and this will not be the same as the area under this continuous curve. If HF is much larger than KBT, your rectangle will start very far off from the origin, and the area under that rectangle will be almost 0. So what Planck had suggested is that energy is quantized. That is, the energy can only take up values NHF. It can have an energy 0, an energy HF, 2HF, 3HF, but nothing in between. So the energy is quantized. And the correct formula to use for the average energy is the following. Delta average value of E must not be given by an integral. Rather, it must be given by a discrete sum. What is the energy? NHF. And the Boltzmann distribution exponent minus what is the energy? NHF over KBT, where n goes from 0 to infinity. And you divide by the normalization, exponent minus NHF over KBT. So this is the average value of the energy. You replace the integral by a discrete sum. देखो यहाँ पे जो फॉर्मूला था E की जगह हमने अब E continuous नहीं रहा, E is quantized according to the quantum number n. This is NHF. यहाँ पे the energy is quantized. It's the same Boltzmann formula, but the only difference is that the energy is not quantized. So as a homework, I would like you to solve this average energy of the mole. And then we put it back in our equation, in this equation. And see, we will get the Planck's formula which correctly describes the results. Now what is the physical significance of the quantizations of energy? The next 20 lectures will describe what is the physical significance
of the quantization. So thank you very much.